It is simple, but not too simple. It uses very little parts, but it accomplishes a lot. It teaches you about capacitive sensing, it has a piano mode, and a few fun little games. And it goes as deep as controlling the music on your computer. And of course, it is fully open sourced. I'm going to show you what this project does. I'm going to walk you through the schematic and the PCB. I will show you how you can order your first PCB and what you need in order to be successful. And I'm going to show you where to get all the components, what it takes to assemble it, and how to flash it. Let me show you what this little board does. It has 5 different modes. By doing a long press on the capacitive sense touchpad, we switch into Pomodoro mode. If you don't know what Pomodoro is, it's basically a productivity technique. Press the first button and it gives you 5 minutes of time before the buzzer begins to ring. Press the second one and it gives you 10 minutes and so forth. But that's not all. Press the second button and hold it and you switch into piano mode. The third mode is a Simon Says game. The more times you can repeat the pattern, the more points you earn. At the end of the game, you get a score. The fourth mode is a reaction time game. You have to react as fast as possible in order to get a point. Under 200 milliseconds, that's what I set it to, which is pretty fast. And the fifth mode is actually pretty useful. It becomes a MIDI controller. You could use it to play and pause music on your computer, set your volume up and down. It's really cool. But none of this explains why this is actually a pretty fun and a very good beginner SMT project. Well, for starters, it doubles as an embedded systems and a project that teaches you how to assemble PCBs. I designed the whole thing to have a very small number of components. But as you saw, quite a lot of capability. I kept all of the passive components at a fair 0603 size, so all you need to assemble this thing is tweezers. And it's a game, it's not a mission critical device, so it's okay to mess up. Oh, and you end up with an ESP32S3 as a platform, which is awesome to tinker with. The schematic is actually fairly simple. Let's go through all of the elements. At the top, we have the USB plug. USB is a differential protocol, so what you have to notice here is that these two wires, they have to be routed together. These wires carry the opposite polarity, so that way when they're combined, it becomes a very strong signal. Then we have 2 resistors, both of them are 5.1K. They're connected to CC1 and CC2. It basically tells the controller, hey, we want to draw power. From the USB, we go into the linear voltage regulator. By default, USB provides 5 volts. On some smart chargers, the actual device that wants to charge can request to switch that voltage to a different voltage, for example 12 volts. In our case, that voltage will remain 5 volts because we are not negotiating any voltages. The 5 volt voltage coming from the USB goes into the linear regulator and that gets dropped down to 3.3 volts. 3.3 volts is required by the ESP32S3. Just an FYI, linear voltage regulators are horrible at power efficiency, but for our purpose, this is perfectly enough. If you are designing a battery powered circuit, then you should look at a boost or a buck regulator instead. Now for the ESP32 circuitry. I'm using the ESP32S3 in a Vroom package, WROOM. There are 2 main things that we have to really take care of when putting down an ESP32S3. The number one thing, we have to put down some capacitors. In my case, I'm putting down a 47 microfarad capacitor, which is pretty hefty. That is going to be used anytime the actual ESP32 requires a surge of power. That's where it's going to get it from. There's basically a buffer, it's a micro battery. That's how you could think about it. And right next to it, I'm putting down a 0.1 microfarad capacitor. The 0.1 is basically used to smooth out any of the ripples coming out from the linear voltage regulator or from the whole entire system. As a rule of thumb, you should always put down a 0.1 microfarad capacitor next to basically any integrated circuit that you're putting down. It will smooth out that power rail quite a bit, and it will make your integrated circuits much happier. And the second most important thing for the ESP32 is the enable pin. The enable pin has to come on after the power. The way we're doing that here is by tying the enable pin to the 3.3 volt line via a 10K resistor with a capacitor right below it. So basically what's going to happen is as soon as you have 3.3 volts, the capacitor will charge first and that voltage ramp is going to be much slower. That way, the ESP32 has enough time to actually charge up its internals and then only then enable itself. The next thing that you'll notice is that we have capacitive sense. These are custom footprints I have designed in KiCad. Here's what they look like. I designed them to be just a little bit bigger than a finger. That way it's easy to press. But here are a few gotchas that you have to keep in mind when putting down capacitive sense. 1. There cannot be any ground underneath or surrounding the capacitive sense. The way a capacitive pad works is by measuring a small increase in capacitance that happens when your finger comes near the pad, and it changes its electrical field. The last thing to notice about the ESP32 is the layout. Notice that I have a keep out zone at the very top of the chip. That's where the antenna lives. In essence, you want to avoid any grounding at all under the antenna or around it. If you put ground right below the antenna, that will literally just destroy the signal altogether. Alright, for the LEDs, I'm using smart addressable LEDs. These are super cool, I love these. You could tell them what color you want them to light up and boom, it goes. But there's a gotcha. Our controller runs at 3.3 volts. The LEDs want to run at 5 volts. So we have to shift the logic from 3.3 volts to 5 volts for the LEDs to be happy. And the last thing to go through is the piezo module. We are driving it directly from the controller itself. The controller has more than enough power to drive this tiny little piezo. The way we're going to control it is by driving a wave on that specific line. That way we could control the notes that we're playing. Now, before jumping into this assembly, I highly recommend that you actually open up this KiCad project, load it up, and change up a few things. Even if it's just as simple as adding your name on the silk screen. And as you might notice, I am not exposing any of the other pads on the ESP32. So what you can do is add some pads, through hole, SMT, whatever. One way to do that is by adding a test point. You can then wire this up to another board or another module or a breakout board. But I'm gonna leave that completely up to you. Let me walk you through how to order the board, what parts do you need to buy, and the tools I recommend. And of course, I'll show you how to assemble it. First things first, there are two ways you could approach this. You could grab the ready package from GitHub. I already zipped it up and it's ready to go. Or if you're going to modify the board, then first thing you want to do is do a design rules check. That will tell you if there's any errors or anything else that needs to be corrected. Maybe you missed a wire that's not connected according to your schematic. Hey, that will check against all of those problems. Once everything looks good, export your files, zip them up, and then we'll upload that package to our manufacturer. Next, PCB makes it super easy to order these boards. Upload your package, make sure you select a NIG finish. Trust me, it's worth the extra money. NIG makes it super simple to work with surface mount components. I literally don't order anything else. The other thing you want to make sure is you're going to get a stencil for your PCB. That will make your life so much easier when it comes to assembly. Then, once we have our boards ordered, go to DigiKey, Mouser, Venkel, or any other distributor and get your components. I have the entire BOM file on GitHub. Literally just take that, copy paste it, order the components. It's super simple. I already did the hard work, so you're welcome. The only thing you will need to add is soldering paste. This is what I use. I like it because it does not require refrigeration like majority of them, and it is low temperature. That means the actual melting point is lower than other soldering pastes. There are multiple ways to reflow your board. One of the ways is a hot plate, the other is a hot air station, or a reflow oven. Okay, and once everything arrives, this is the fun part. What I love to do is print out your entire BOM. That way you have all of the part numbers, you've got all of the positioning, and you've got everything on a physical piece of paper. Make sure you have all of the components that you need before you start. Trust me, this is a big one. I've done this so many times where I go in, I start my assembly and then realize, oh no, I don't have a component. So don't do that. Just make sure you have all your parts. Now, what I like to do is create some sort of a jig. I usually use these little plastic pieces, but you can actually create a jig that holds your PCB with literally other PCBs. Line up your stencil so every pad is perfectly aligned. I use Kapton tape to hold the stencil in place. Spread your paste as evenly as possible. You don't want any big buildups or anything like that, just an FYI. And you want to make sure that every pad is actually covered. Then take out the printed BOM and go through every single component and place it with tweezers. That's all it is. Make sure every component is sitting nicely in the paste. Once you go through every single line item and you make sure that all of them are populated as they're supposed to be, all you have to do is reflow the board. If you're reflowing with a hot plate like I am doing here, and if you're using the low temperature solder that I recommended, I set my hot plate to about 180 degrees. Place your board on top, turn it on, and wait. But watch it carefully, because you will see the paste go from a really dull gray color to a beautiful shiny silver. And as soon as it does, switch it off. Let it cool down. Do not touch it, it's really hot. Oh, and if you're using a hot air station, just make sure you don't concentrate in one single spot by holding it in a single tiny little area. That's the worst way to reflow. What you want to do is go in circles and make sure you heat things up nice and even. And again, I'm about to drop a whole entire surface mount masterclass here on YouTube, so subscribe. But okay, if you made it this far, we are almost at the very end. And then it's time to actually program the thing. Press the boot button and connect it to power. If you don't see any magic smoke come out, that's good news. You could load up the firmware in multiple different ways. You could compile from scratch or take the binaries from GitHub and just drop it in using that ESP32 tool. Load up the binary, watch it come alive, and that's it. If this is your first surface mount project, congratulations, because that literally is it. That's all it takes. I hope you learned something, and I will see you in the next one. Bye.